China has developed a breakthrough stealth coating made from one of the most unexpected materials ever used in advanced aerospace, loofah. This natural fiber, once carbonized and enhanced with magnetic nanoparticles, can absorb over 99.99% of Ku-band signals while reducing reflected radar intensity by nearly 700 times. At just 4 millimeters thick, this new composite could reshape how future low-visibility aircraft and sensors are built. The story begins with an unusual idea. What if a simple natural plant structure could outperform complex man-made materials in absorbing electromagnetic waves? That question inspired researchers from the People's Liberation Army, PLA, and the China Aerospace Science and Industry Corporation, CASIC, to look at the loofah plant, which has a uniquely porous, sponge-like structure. Once dried, loofah is made of a three-dimensional network of cellulose fibers, arranged in a natural labyrinth. What makes this structure interesting is its ability to trap and scatter waves inside countless tiny channels. The research team began by carbonizing dried loofah, heating it to high temperatures until its cellulose skeleton transforms into a lightweight conductive carbon scaffold. Instead of disintegrating, the loofah becomes a strong yet ultralight maze of microtunnels, ideal for disrupting incoming electromagnetic signals. But carbon alone wasn't enough. To boost the material's performance, scientists embedded it with nickel-cobalt oxide nanoparticles, Ni-Ca2O4, which have exceptional magnetic properties. This combination resulted in a composite material the team named NCO2, created through hydrothermal and carbonization processes. What sets NCO2 apart is its extraordinary efficiency. Despite being only 4 millimeters thick, about the thickness of 2 stacked coins, it absorbs more than 99.99% of electromagnetic waves in the Ku band, which ranges between 12 and 18 gigahertz. This band is especially important because it's used by high-resolution monitoring systems, including advanced surveillance satellites. According to the research published in High-Power Laser and Particle Beams, the material's structure forces incoming waves to bounce endlessly within its pores, losing energy with every reflection. The carbon network then converts this energy into harmless heat through conductive loss, while the magnetic nanoparticles enhance absorption through magnetic loss mechanisms. Through the combined processes of interfacial polarization, dielectric tuning, and impedance matching, the material reaches levels of absorption that outperform many synthetic composites used today. To understand how NCO2 reduces reflected signals by nearly 700 times, it helps to look at how electromagnetic waves normally behave. When radar waves hit a surface, several things can happen. They can reflect, scatter, pass through, or be absorbed. Traditional coatings aim to absorb as much energy as possible, but they often struggle to handle different frequencies or maintain performance when waves come from different directions. The loofah-based composite solves these challenges through its natural 3D mesh, which the researchers describe as a microscopic jungle. When electromagnetic waves enter this labyrinth, they don't bounce off immediately. Instead, they travel deeper into the structure, encountering countless intersections, pores, and fiber surfaces. Each internal reflection reduces the wave's strength bit by bit. This process is known as multiple scattering. What makes NCO2 exceptional is its engineered combination of structural and electromagnetic properties. The carbonized loofah forms a conductive network, allowing electrons to move freely. These moving electrons dissipate microwave energy as heat, a mechanism known as conductive loss. Meanwhile, the nickel-cobalt oxide nanoparticles introduce magnetic loss, another pathway that drains wave energy through interactions between magnetic dipoles and the electromagnetic field. The research team explains that the synergy of these mechanisms creates optimized impedance matching, meaning incoming waves are not strongly reflected at the surface but pass smoothly into the material, where they are systematically weakened. This matching is critical in stealth materials, because even a powerful absorber is ineffective if waves cannot enter it in the first place. The outcome is remarkable. Radar reflections measured in the Ku band were reduced to less than 1/10,000th of their original intensity. In practical terms, a vertical radar cross-section, often the most challenging angle for stealth, could shrink from 50 square meters to under 1 square meter. Even waves coming from directly above, such as those used by space-based radar platforms, experience the same level of absorption. This is a major milestone because overhead detection is typically the vulnerability of conventional low-visibility designs. The potential applications for a material like NCO2 are extensive, especially in technologies where low visibility is essential. For advanced aircraft, reducing reflected signals by nearly 700 times means improved performance in areas monitored by high-resolution sensing systems. Surveillance satellites operating in the Ku band can detect fine details, so a coating capable of absorbing over 99.99% of signals in this range represents a significant advancement. Beyond aircraft, the coating could be applied to uncrewed aerial platforms, sensors, or other equipment requiring low observability. The material's extremely low thickness, only 4 millimeters, makes it easy to integrate without affecting aerodynamics or adding significant weight. Its biomass origin also introduces advantages for sustainable production, since the base material is inexpensive, renewable, and naturally abundant. The research team emphasizes that this innovation provides a foundation for developing green, sustainable, high-performance electromagnetic absorbers. Traditional materials rely heavily on synthetic polymers, rare metals, or hazardous chemicals. Using a carbonized plant structure avoids many of those limitations, while offering performance that matches or surpasses more complex composites. Another key aspect is adaptability. Because the underlying architecture comes from a natural plant scaffold, variations of the process could create materials tuned for different frequencies. By adjusting the density, adding different nanoparticles, or modifying the carbonization temperature, researchers could create coatings optimized for other bands used in monitoring systems, such as X-band or Ka-band technologies. The performance validation using COMSOL simulation software confirms that the material's electromagnetic behavior is not just theoretical. The team demonstrated that the loofah-based composite maintains its absorption even at steep incidence angles, meaning it works consistently even when waves approach from awkward directions or at sharp vertical angles. This reliability makes it suitable for a wide range of future platforms. China's loofah-derived NCO2 composite represents an unconventional but highly effective approach to reducing electromagnetic visibility. By leveraging the natural 3D network of the loofah plant, carbonizing it into a conductive scaffold, and enhancing it with magnetic nickel cobalt oxide nanoparticles, researchers achieved a material capable of absorbing over 99.99% of Ku-band waves. Its thickness of only 4 millimeters and ability to maintain performance even with overhead signals make it an important development in advanced materials research. The science behind its performance shows a blend of natural geometry and engineered enhancements, multiple scattering, conductive pathways, magnetic interactions, and impedance matching. This combination allows NCO2 to weaken incoming waves through several internal mechanisms, reducing reflected signals nearly 700 times and significantly lowering apparent radar visibility. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries, and don't forget to leave a comment below. Also, you can visit our website, SpaceEyeNews.com. Thank you for watching, and see you next time.